5.2, we're dealing with logarithmic functions and their graphs. So 5.1, we dealt with exponential. Okay. 5.2, we're changing gears to go on logarithmic. Logarithms are the inverse to exponential. What? What? They're inverses. So in 5.2, we're going to recognize and evaluate log functions with base A. We're going to graph log functions, recognize, evaluate, and graph natural log functions, and use log functions to do word problems. In 5.1, we dealt with exponential functions. F of x equals a to the x power. F of x equals a to the x is an exponential because the exponent is the variable. Okay. An exponential function does pass the horizontal line test. If a function passes the horizontal line test, that makes it 1-to-1. And if a function is 1-to-1, that means it has an inverse, right? The inverse to this function are the logarithmic functions, base A. So some things that must be true for logarithmic functions. X has to be greater than 0. A greater than 0, but not 1. And this is what a logarithmic function looks like. Y equals log base A of x. That is a logarithm. That means that x is equal to a to the y power. Notice this statement here. If, right? If and only if means that sentence is true whether you read it forwards or backwards. Okay. Here it says f of x equals log base a of x. That is read as log base a of x. This is what I said. Okay. I want you to notice that in both of these equations, the base is a, right? When you raise something to a power, the item that's being raised to the power is called a base, correct? So a is raised to the y power. Over here, my base is a. And I'm going to say it again here in a minute, but a logarithm is an exponent. So if I take the logarithm of something and get an answer, notice that y is my exponent in a to the y power. So the base is a. Moving on. Which means y equals log base a of x is the same thing as x equals a to the y power. The first equation is logarithmic form. The second equation is exponential form. Here are some examples with numbers in them. If I told you that 2 was equal to log base 3 of 9, what is the base? 3. What is the exponent? 2. What is 3 squared? There it is. Okay. So 2 equals log base 3 of 9 is equivalent to 9 equals 3 squared. Sometimes I'll write this. Log, here's my base. This is very, very high-tech technology or vocabulary, so hang on here. This is a thing. And this is a power. Okay. I'm taking the log of something. The base is my base. The answer is the power. So that would mean that the base raised to some power equals what? The thing. Okay.
Wait, so are log and the thing the same?
Look, base, base, power, power, thing, thing.
Oh, okay.
They're inverses of each other. So 5 cubed, if 5 cubed is 125, what's the base? What's the power? What's the thing? Base is 5, power is 3, thing is 125. I wrote it as a log statement.
I could definitely just cheated.
I know. It's very important that you understand how to go from exponential to log and from log to exponential. Okay. When evaluating logarithms, remember that a logarithm is an exponent. I said that a while ago. This means that log base a of x is the exponent to which a must be raised to obtain x. This is just words based on the equations we've just looked at. For instance, log base 2 of 8 equals 3. 3 is the exponent, right? 3 is the exponent. 2 is the base. What is 2 to the third power? 8, right? All right, let me wipe this out real quick and we're going to work through this. Nice. Evaluate each logarithm at the indicated value of x. So letter A. I guess I'm going to write in purple now. F of x equals log base 2 of x. This is asking you, what is f of 32? F of 32 is equal to log base 2 of 32. What is the base? 2. What is the power?
32.
This is the power. We don't know the power. This right here is going to be the power. 2 to what power equals? What's the thing?
32.
32 is the thing. High-tech vocabulary. I'm sorry, deal with it. 2 to what power is 32? Fifth power. Yep. F of 32 is equal to 5. Part B. F of 1 is equal to log base 3 of 1. This is what I'm looking for. What is my base? 3. What is the given power? They didn't give me one. I could have put a y there if you wanted to. That's fine. Okay, but what is this going to equal?
1.
Okay. What's the answer? 3 to what power is going to be 1? 0, because anything raised to the 0 power is
1.
so F1 is 0. Part C. F of 2 is log base 4, 2. What is the base?
4.
4. What is the exponent?
Don't know.
That's what we're trying to figure out. What does it equal?
2.
What's the answer? Why? Why is it a half?
Because I'm doing a square root. Or like whatever.
Okay.
Like that's
What does an exponent of 1/2 mean?
like it's square root.
Square root, right? What's the square root of 4? Okay. So f of 2 is 1/2. And D, we have f of 1/100 equals log base 10 of x. What is my base?
10.
10. What is the power?
Don't know.
We don't know yet. What does it equal to? That's not supposed to be an x.
1/100.
That's supposed to be 1/100. Okay. So 10 to what power is going to give me 1/100? -2 is correct. Okay, I'll talk about that in just one second. Let me write it down. Okay. 10 to what power is 100? 10 squared, right? 10 squared is 100. How do I take 100 and make it go to the denominator? Negative exponents.
Because whenever it passes through the curve,
Yeah.
you get it.
As soon as I pass through a fraction mark, so if I have 100 right here, and I want to take this 100 from the numerator to put it in the denominator, I need to have a negative exponent, because a negative exponent makes it move. So if I put a -2 right here, that means, oh, negative, drop it to the bottom. That's 1 over 10 squared. 10 squared is 100. That's 1 over 100. Okay. Snap this if you want it. I'm about to delete everything on the slide. Okay. Nice. Get out of the way. So there is A and B with the book working it out. I talked through it though. There's C and D. Questions so far? Anyone? Anyone? Properties of logarithms. And what is a log? The logarithmic function with base 10 is called the common log. It's denoted by log base 10 or simply log. So here's what I'm saying. If you see me write that, what's the base? You see a base here?
There is no base.
Okay. If you don't see a base, what is it? It's 10. Okay. Because that's a common log. Look at your calculator. Look at the key that says log on it. What do you see if you press second log? What's above the log? 10 to the x, right? So that's telling you that those are inverses, right? So 10 is the common logarithm. It's the same reason if I was to write this. What's the index? I don't see a 2 up there. But there is one there, right? It's assumed. Just like if I was to write x, y to the 5th power. What is the exponent on the x?
1.
I don't see a 1 there, but we know it's there. Okay? It's the same concept with this whole common log. So if you just see log, know that that means base 10. Here are some properties of logarithms. Log base a of 1 is equal to 0 because a to the 0 power is 1. Log base a of a is 1 because a to the 1st power is a. Log base a of a to the x power is x because a to the log base a of x is equal to x. Because logarithms cancel out. Notice right here, I've got log base a of a, but my exponent is up here. Once I started with an exponential, a to the x. If I have an exponential, a to the x, and I take the log with the base of that same number, basically, log base a of a cancels, leaving me with just the x. That's why they're inverses. So to get a variable out of the exponent, you take the log. And the last one says, log base a of x is equal to log base a of y. That's only going to be true if x and y are the same. That's your one-to-one property. We're going to see these exact same properties here in a little bit with a different base. But these properties are true for all bases, aren't they? That's why it has base a. A can be anything, okay? To sketch the graph of y equals log base a of x, you can use the fact that the graphs of inverse functions are reflections of each other over the line y equals x. Okay, we're about to go back in time to yesterday. I have a coordinate grid. I want to graph f of x equals some number, I don't care what it is, to the x power. Do y'all remember what that looks like? Okay. Over here, it's close to 0, right? And it's slowly increasing, slowly increasing, slowly increasing. And all of a sudden, what's that value right there?
0, 1.
0, 1. I don't care what A is, that's still 0, 1. And then what happens as soon as it passes that point right there? It takes off, right? That's what we talked about yesterday. Well, an inverse function is a reflection across the line y equals x. So here's the line y equals x. I want to graph g of x equals log base a of x. These two functions are inverses. Can you tell what it's going to look like if I reflect it across that line? Is it down here? What's that point right there? 1, 0, right? Because if they're inverses, x and y switches. And then it's going to, okay. Does it appear that that red and blue graph appear to be symmetric about the line y equals x? There you go. Okay. Okay, so the next slide, I'm not going to do what it says because in a sense, I've already done it. Okay. This could represent any value of a, right? This could be 2 to the x power, right? This could be 5 to the x power. Is that right? Okay. This could be log base 2 of x. This could be log base 5 of x. Does that all make sense? Okay, so the next slide, I'm just going to pull it up. It says to graph 2 to the x and log base 2 of x on the same graph. Are y'all okay with the fact that I just did that? Okay. If you were to plot points, this is what it might look like. Notice if we're graphing 2 to the x power, the point -2, 1/4 is right here. What happens if you swap those? You get 1/4 -2, which is right here. So this graph here is the inverse of all these, swapping x and y's, right? Moving on. Because log base 2 of x is the inverse function of 2 to the x power, the graph is obtained by plotting the reverse points. And those graphs are reflections. And I think my graph is almost as good as theirs. The nature of the graph in figure 5.11 right below is typical of functions in the form f of x equals log base a of x, where a is greater than 1. They have one x-intercept, one vertical asymptote. Notice as soon as it passes the x value of 1, it continues to increase, but very slowly. Okay? Yay. Characteristics of log functions. To graph log base a of x, where a is greater than 1. Remember that this is the inverse of what we did yesterday, right? What was the domain of an exponential? If you're graphing an exponential, what can x be? Anything, right? So on exponentials, the domain was -infinity to +infinity. But if functions are inverses, that means x and y swaps. Notice the range of exponential. It was the domain of exponential, right? I think I said the same thing twice. The range of logarithmic is the domain from exponential. The domain of logarithmic is the range from exponential. The x-intercept is at 1, 0. The function is always increasing. It is 1 to 1, therefore it has an inverse. The y-axis is a vertical asymptote. The function is continuous, and it is a reflection of y equals a to the x about the line y equals x. The basic characteristics of the graph f of x equals a to the x are shown below to illustrate the inverse relation between f of x equals a to the x and g of x equals log base a of x. And this is kind of the stuff I've already talked about. How about e to the x? We talked about it yesterday, right? E is just a number. So e to the x is exponential. The inverse function of e to the x is called the natural logarithmic function. To write the natural logarithmic function, we're not going to write log base e. We're going to write ln, or natural log of x. And in case you don't know, this can be read ln of x. When I saw this the first time, I was like, what is this? Okay. Notice down here. Here you see log base e of x. You're not going to see it written like that. Very, very rarely will someone do that. If the base is e, they're going to write it like this. And you just have to know, if you see natural log or ln of x, you need to know that the base is e. I always do it in script when I'm doing it, so it doesn't look like a 1. Oh, I don't know, but because it's not a capital, they're not capitals. Just to give you something to graph about, and it works. The above definition implies that the natural logarithmic function and the natural exponential function are inverses of each other. So every logarithmic equation can be written in an equivalent exponential form, and every exponential equation can be written in the equivalent logarithmic form. We can go back and forth. So notice this. Y equals natural log of x. What is the base? Y equals natural log of x. E. What is the power? Y. What is the thing? X. So x equals e to the y. Okay. Just like we talked about with logarithms, this is just another base, folks. They're mirrored about the line y equals x as well. Xavier, do you stand? Or do I need Jacob just kind of pop you in the back of the head? I'll just kind of nod at him. And if I give him the nod, he knows from now on, if I do this, you just reach up and Will Smith him.
One of these days you're gonna be explaining something and you're gonna nod.
No, I didn't mean it that time. Okay. Use your calculator to evaluate the function f of x equals natural log of x for each value of x. So letter A, all it's asking you is, what is the natural log of 2? Can you type that in your calculator? Natural log of 2. Okay, you get about
0.3. That's not what I got. I got that, but not that. That's what I got. You just hit ln.
hit the natural log button.
Okay, where the on button is, go up 2.
Okay, so the natural log of 2 is about 0.7. Guys, I am rounding. The next slide is going to show the answers spread out. Okay. Natural log of 0.3.
-1.2.
Does that make sense? That it's negative.
Yeah.
Think about what the function looked like. It was down here. As soon as it got to 1, 0, that's when it hits the x-axis, right? And then it's continues to increase. What's the natural log of -1?
I.
Mm-mm. Does not exist.
Does not exist.
Yes.
It
I've
says
been
it on
struggling to figure out what that means for the longest time. I'm like, what's the point in this?
Okay.
It literally says if an answer does not exist. but it-
D and E. If the answer does not exist, D. Okay. Guys, when we talked about logarithm functions a while ago, we specifically stated that x must be greater than 0. -1 is not greater than 0. Can you use 0? What's the natural log of 0? What do you get? Natural log of 0. Type it in. No, because x has to be greater than 0. You want a really big negative number? Do natural log of 0.001
You can't do it. Oh wait, no, you can't.
-6.9.
times 10 to the.
Oh wait, how many zeros did you say?
I had a couple zeros.
I only put
I
in
typed in like 12
Okay.
zeros, and we had -27.
You got to put a decimal first.
Oh, you're right.
Okay. So what? How about part D? What is the natural log of?
You just like put that in. You just put that, and then it's 0.89. I'm pretty sure it's
See, I told you there was gonna be something so.
Okay, I'm just rounding consistently. Okay. Now, folks, pay attention to your homework. I was working with a student earlier today. He kept getting it wrong, but he was right. The instructions clearly said to round to 3 decimal places. He was using 1 decimal place. Guess what? It's wrong. Okay. Say next slide here, the answer is not rounded.
Error. I got syntax.
Okay. I'm not going to spend much time on this slide, folks. This slide is exactly the same as the one with logarithms a while ago, but this one's specifically for base E. The other one said log base A of 1 is equal to 0 because A to the 0 power is 1. Aren't we saying the same thing here?
Yeah.
Okay. E is just another value of A.
I just have to remember the different logs, but
Okay, students participating in a psychology experiment attended several lectures on a subject and took an exam. Every month for a year after the exam, the students took retests to see how much of the material they remembered. How much are you going to remember of this lesson next week? Next year?
Definitely none.
Tomorrow?
Maybe a little.
About the same as next year.
Can I put it in my calculator?
Let's do this problem tomorrow. Let's wrap this because it's 2:11 right now. Yeah. Yeah. So we'll wrap. This is the last problem for this. So we'll wrap this up tomorrow, and then we'll jump right into 5.3.
I think.
I just say we don't.
Wait till we got a little bit.
The weather might change.